Okay, everyone, our final presentation of this session entitled Combustion and Gasification of Pellets Produced from TORWASH. And this will be presented by Eddie O'Callaghan, joining us online from Ireland. Eddie holds a degree in Chemical and Process Engineering from Munster Technological University, Ireland, and has over 20 years of international experience as a technical director and chemical engineer. Eddie is the founder of FQ Partner Heat Systems, who design, manufacture, and commission state-of-the-art thermal processing solutions. So, Eddie, are you there?
Yeah, I'm here. Can you guys hear me okay?
Yeah, we can hear you fine. Okay, Eddie, the floor is yours.
Perfect. Thanks for that generous introduction. Okay, guys, my name is Eddie O'Callaghan, as has just been pointed out, and I represent a company called Heat Systems, who's worked on this project over the last couple of years. And over the next 20 minutes, we'll have a look at some interesting results, specifically looking at the thermal processing trials that we did for paper, orange, and waste olive pellets. So just to jump right in, this is our lab, and this image here you can see the basic material flow through our indirect fired rotary kiln, which is at laboratory scale in our facility in the west of Ireland. And in this image, all the surrounding ancillary equipment and platforms have been removed, just to give you a clearer picture of what's going on and the material flow. So in the center of the image, you see this black rectangular box. This is the kiln. So within this box, it's an insulated system, and we have a rotating tube, and this tube is designed to go up to nearly 1,000 degrees C. And the system is really actually quite simple. So what we do is we feed material into the hopper, and this can be pellets, it can be biomass of different descriptions, and we maintain a hopper head very simply to keep air out, because what our typical intention is to induce pyrolysis rather than direct combustion. And then we feed the material into the system through this long feed screw here, and that's fed in at a controlled dosing rate. So what we want to do is control the feed rate and control the bed depth and control the residence time and the spin of the tube within the kiln. So material progresses down the tube over a period of time. It's exposed to our temperature set point. The material degrades and breaks down into gas and solid, and the solid is typically char and ash. The solid material exits the system at the back, at the bottom here, and the gas exits at the top. Now, because the gas is typically flammable, we combust it for safety purposes before we emit it to the atmosphere via our stack. But also we have a sampling infrastructure in and around this area at the back here, so we can test the gas species prior to combustion. We could also test it post-combustion. So this is just a little example of one of our sample points. It looked quite small. We actually increased the size later on. And this is another sample point post-combustion, a little bit higher up. So we have temperature probes dotted around this system to give us tight control of the process, and they're also required for safety. And they allow us to control the performance of the system. But probably the most important probe is the probe we have here inserted at the back, which goes directly into the machine, into the tube, and actually contacts the internal bed. So this is really what we're trying to control. We're trying to control the actual material in the system and keep it maintained at our temperature set point as far as practical. Now, we also have some temperature probes elsewhere, just to give you an idea. Here's a temperature probe that was up on the afterburner. Okay, so that's just to give you a bit of an overview of the system we use for the trials. But I think, as we all probably know here, transferring from lab scale to commercial scale is often a huge challenge. And we're very conscious of that challenge. One of our goals as a company is to jump that gap, that technology readiness level gap, and get systems from lab scale right into commercial scale. And one of the approaches we use for looking at scale up is we focus on this concept called a Freud number. This particular number is important for rotary systems, particularly rotary kilns. And what it is it's just a ratio of centrifugal forces and so on. But what it allows us to do is to mimic conditions at lab scale as to what we would expect at larger scale. So we can have reasonable certainty that what we do at the lab scale is actually going to be representative of what we're going to do at a larger scale, and that underpins our validation of the process, etc. So, for example, in these trials, looking at this Freud number concept, what we wanted to do was to spin the tube at a certain RPM that would give us a certain Freud number, which we also felt would be appropriate for the larger scales system down the road. So we were focused on generating this rolling regime within the tube. So here you can see a cross section of the tube. And the reason we like to have a rolling regime is because we feel it's a nice balance between mass transfer, movement, agitation, while not moving further to the right-hand side here, which would be, say, you're heading towards becoming a centrifuge, which is not necessary, quite costly for what we're trying to do, and not practical at a larger scale. And at the same time, we don't want the tube rotation to be too slow. You know, we don't want the bed to be slumping or sliding, where we're not getting good mixing, we're not getting good reactions occurring, etc. So we wanted to focus on keeping our trials in this rolling regime, which in theory then is a Freud number between 10 to the minus 4 and 10 to the minus 2. So in conjunction with that, what we also wanted to focus on, a key parameter for us, is what residence time does this material need in order to thermally break down into beneficial outputs like syngas for energy production or biochar, etc. So we use our own proprietary kinetic model depending on the type of particle, the size of the particle, the density of the particle, etc. The bigger the particle, the more time it typically needs to break down in the system. So using our own analysis, we were able to estimate as a starting point 45 minutes to be appropriate residence time for the paper and for the orange pellets. Now, when we looked at the olive pellets, because they were a little bit more dusty, not quite as robust, smaller particle size, our feeling was 30 minutes would have been a better residence time. Okay, and also the feed rate, what we could see to give us a bed depth of around 13%, which we felt would be appropriate for these materials. We thought a feed rate between 3 and 4 kilos an hour was ideal for this set of trials. Okay, so here we can see some of the settings that we used at small scale for the paper pellets. So on the left-hand side here in the trial kiln, we can see the key parameters that we took. Our target temperature of 700 degrees, 45-minute residence time was our target, as well as the 13% bed depth and a rolling motion regime. So as we just discussed, the Freud number of 0.00126. Now, when we compare this to scaling up in the future, what we're looking at here is if we were going to a larger system, something we're calling a TR1200. Now, this is our own models, okay, for kilns, but what this is a system with a 1.2 meter diameter tube, which is 7 meters long. So if we were to use a system at that scale, all else being equal, what this is saying is that we can get 550 kilos an hour through the system. And similarly, if we wanted to go even bigger again to the next level, if we went to a 2.1 meter diameter tube, 12 meters long, we could get 2 tons through the system. So what's this all mean? Look, this is all quite important if we're doing a business case for a commercial scale. So if we're looking at paper pellets at commercial scale, and somebody said, right, how many tons an hour can we get through that system? What's it going to cost? We can do a complete business case and analysis based on the trial results that we did. Okay. So our basic mass balance here shows that we achieved good results with the paper. Now, we did see an awful lot of ash, as you would expect with paper, close to 25%, which is huge. And also, we didn't see a huge amount of volatiles, which translates into the syngas that we're getting off, which can be used for energy production, etc. But what we did see was a very good conversion. So, for example, the theoretical best conversion out that we could estimate based on doing approximate analysis of the material. And this is just to say that the ash content plus the moisture content, if that's all you had remaining with perfect pyrolysis conditions, you would expect about 39% coming out. So we were coming in at around 46%, I believe, which to us was indicative of reasonably good pyrolysis based on the settings that we estimated, which is the 45 minutes residence time to 700 degrees C and the 13% bent depth. Okay, so these are temperature readings that we took during the trial. 6 readings. The most important reading is the blue line here in the middle. And this is really just showing that we were looking to track 700 degrees continuously for the bed within the tube. And we remained pretty close to that 700 degree mark. This red line here, this wobbly line, is the afterburner temperature, which we're not so concerned with. We were playing around with the air to the afterburner to keep it cool for practical purposes at the scale that we were operating. So that went up and down a little bit. But generally speaking, we had quite consistent temperature readings across the board, which we were very, very pleased with. And this slide really is just looking at some observations that we took at various points during the trial. So specifically for paper, we noticed a lot of ash, which tended to turn into dust in the gas phase. And this dust tended to coat the instrument probes that we were using for analyzing that gas. Now, this is vitally important, this type of information, from a practical perspective. Again, if we're keeping one eye on commercializing these systems, what this is telling us is, look, we probably need some sort of dust dropout box, possibly a cyclone, possibly a baghouse, or some sort of technology to deal with the ash if we're going to commercial scale with paper pellets and generating syngas. Yeah, so look, these little insights, even though they could be missed during a trial, by documenting them, putting them down on paper on the log sheet, they could become very important when trying to scale these systems. This slide here is just to show that we also tracked energy consumption for the system, which is useful in determining the OPEX, the operational cost of a system at larger scale. But for us, during the trials, it was simply an indication that the energy input was pretty stable during the operation, which is indicative of a reasonably good, stable operation. We didn't see any major energy surges. We didn't see any major drops. All of this is indicating that the trials went pretty smoothly and operated quite stably. Now, this is just a view of our site glass on the afterburner. So this is showing the syngas that was coming off the bed material. And we obviously combusted this syngas for safety. And really there was quite a lot of energy, heat coming off the syngas that we were generating, even though we were only operating at 3 to 4 kilos an hour. Really, there was quite an amount of heat coming off that gas. And actually, in the next slide, I think we have a little video which might show it a little bit more clearly. Okay. So you can see there's quite a bit of activity during these trials. That was just a quick snapshot that I randomly took in the middle of the trial with my camera phone. And there's a lot going on just to make sure that every reading's been looked at. The gas analysis has been done at the correct time. The feed is consistent. We're not having bridging or blockage issues. So yeah, it was quite an intense operation. So in that video, you can see some of the equipment that Johan and Marco from TNO had set up for analyzing the gas and for also condensing the tars in the gas. So you might have seen a water bath there. So quite a bit of infrastructure was set up, and the guys did an excellent job in monitoring the gas quality throughout the trials. Oops. Okay. So on this slide, you can see the paper pellets that we received on the left. So these are the pellets essentially coming out of the TORWASH system and following CPM pelletization. And these were really good pellets to handle. There was very little dust, very robust. They retained excellent shape. And on the right-hand side is the remarkable transformation of the pellets into a consistent and robust char material. So this really highlights the effectiveness and repeatability of the process. Okay, so in summary, I can say that with the paper pellets, our performance was stable. It resulted in a good conversion and easy processing. But as noted earlier, cleaning of the gas sample probes was continuously required to remove the char buildup that we were seeing. So it's just something to be aware of for a larger operation. So now if we look at the olive, we applied similar conditions as we did with the paper pellets, but reduced the residence time from 45 minutes to 30 minutes on account of the finer, dustier nature of the feed. As we predicted that we could reduce the residence time by roughly 30% based on some of our analysis. And if we look at the composition of the olive pellets, what we saw was a very high volatile content. Essentially, this feed was acting like rocket fuel in terms of generating syngas and the energy content within that syngas. And we also saw very low ash in this material, very low moisture. And we were able to achieve very good conversion. So we were getting about 18% out when we were predicting perfect conversion to be in around 15%. So this is a good indicator to us that the settings that we had estimated at the outset for residence time, temperature, rolling regime, etc., feed rate, are very appropriate for achieving conversion with this type of material. Here are the readings we took with the olive. Very stable again. The blue line here, which is the internal bed temperature, was very close to 700 degrees at all times. Here you can just see it a little bit closer. And it's worth noting, in these images here, we can see the condition of the olive pellets. And as you can see, there's a lot of dust and fine material in there. And we did experience compaction blockage issues in the feed screw because of the nature of this feed. Now that's more likely an issue at the smaller scale that we were operating at, where bridging and stickiness and compaction typically are amplified as problems. We wouldn't necessarily see this as a problem we would expect to see at the larger scale. So in summary, performance was steady with the olive pellets once we resolved the feed issues. And we did have some thoughts during this process. We were looking at the material and we felt perhaps maybe it could benefit from blending with other materials to perhaps give it a more robust nature, or alternatively paying more attention perhaps to the moisture content, the oil content of the waste olive material prior to pelletization. But in any event, we saw huge volumes of gas coming off, high energy gas, and what was apparent to us that if we were to go to a larger scale with this material, we would have to pay close attention to ensuring that we upsized and ensured we had adequate sized gas conditioning equipment. So this could be gas scrubber, it could be the pipe work, it could be the subsequent engine converting the gas into electricity. But certainly because of the volume of gas that we did see, you know, you couldn't take a chance undersizing the back end equipment. So that's where you would really focus some of your money. In relation to the orange pellets, we went back to a 45-minute residence time because the pellets were very similar to the paper pellets and they were denser and bigger than the olives. But all else more or less was equal. So what I'll probably do is skip through the next few slides a little bit quicker because it's quite similar to what we saw for the paper. We achieved pretty much a perfect conversion with the settings that we're choosing. Again, maybe that was a little bit lucky, but it's always nice to validate the assumptions that we had taken initially with the material. Again, the primary temperature of interest, the blue line here, once we got up to temperature, we were tracking quite closely to our target of 700 degrees. And the red line here, which dropped significantly, that was the afterburner temperature. So we were seeing the afterburner going up to nearly 1,000 degrees C. So we were just a little bit concerned at our scale that we were going to overheat it. So we brought on a lot of secondary air to help cool it down. What's of interest here, just to show you, one of the readings we took, now we were continuously monitoring the composition of the syngas from these trials, but just as an example, I've shown one reading here at this point in time. And as you can see, we had roughly 14% methane in the syngas, with 14% hydrogen, 19% carbon monoxide. Now these are high energy content gases, and this is very important information if we are specifying downstream equipment. For example, a scrubber vendor would be very interested in this information, but more importantly, if we were going to a gas engine generating electricity and heat, this is the first question a vendor would ask, you know, so what is the composition of the gas? It completely changes the nature of the engine, the spark plugs, how the engine would operate. So to have this information locked in and very clear is quite important. So yeah, as you can see, the gas quality is quite good. And another good indicator for us that pyrolysis is operating correctly is the absence of oxygen or a very low oxygen content. So you can see the oxygen content was 0.27% there, which is extremely low, which we're very pleased with. And particularly when you're operating at a smaller scale, you know, there can be a tendency for some tramp air getting in, and leaks and so on, but this is indicating to us that you know, we were getting very good pyrolysis conditions. So here's an image of the orange pellets. And you can see there's very little dust. It's very different to the olive material that we received. Very good shape and just very easy to handle. And this then created a very easy to handle biochar. Again, yeah, we saw stable performance, which is indicative that the settings were good. There was really no issues with this material. Okay, so we're probably coming to the end of the presentation now. And I guess, look, if we step back a little bit and think about what are the conclusions that we can draw from these trials. Well, look, personally, I believe there's a significant opportunity to integrate TORWASH technology at the front end of a process. Obviously, there's a few teething issues and perhaps some learnings, but I can certainly see the TORWASH at the front end of a process with perhaps anaerobic digestion in the middle of the flow sheet, with a pyrolysis system at the back end. Now, I personally believe this can be done at commercial scale now throughout Europe in a decentralized fashion, close to waste sources, in local areas, and the possibilities are quite vast, including energy production, fertilizer production, biochar production, which is probably an area that's growing rapidly, and maybe we haven't focused on so much here in this conference, but I can absolutely see that as being an option. And of course, waste management is another key area. So this flow sheet here is just an example. It's by no means the only possibility, but you could, you know, if I just run through it briefly, the main points. If we had a back-end pyrolysis system, as shown down the bottom, we could potentially run it off biogas coming from an AD system, a portion of biogas to run that. That in turn has been fed with either pellets from the TORWASH system or simply dehydrated biomass, even if there's probably a very good opportunity not to pelletize depending on the feed type. That gets fed in. That allows us to create a biochar or a high quality renewable fuel. And the syngas and the waste heat coming out of the system can either be recycled back into the drying step, or alternatively that is fed to a separate gas engine to generate electricity and heat. So there's lots of options, lots of ways to do it. But ultimately, the three core items would be TORWASH, anaerobic digestion, pyrolysis. And to my mind, that is the optimum economic system. Okay, so with that vision in mind, I guess, I just want to say quickly that we're building a commercial pyrolysis plant at the moment ourselves. Here's an image of our kiln being offloaded in our plant in the west of Ireland. And this machine here is capable of processing up to 2 tons per hour, depending on the feed type. And it's a proprietary custom design, but it's perfect for biomass feed types, which we've just looked at here. It is absolutely perfect. And this embarrassing photo here, right, is just me to show you as a reference, just to give you an idea of the scale of the systems that we're using at the moment, and we're currently moving quickly towards commissioning. Now our site in the west of Ireland is permitted to take over 189 different waste types, both hazardous and non-hazardous. Again, this image here is just to give you an idea of scale. And this image here is the heat tube, which is the heart of the process. And so this tube rotates, and I hope maybe you can visualize and imagine either pellets or different types of materials working their way down this tube as it rotates, probably 2 RPM or something along those lines, 700 degrees. And you can see the lifters within the tube are there to gently agitate and lift the material and promote beneficial pyrolysis reactions. So this particular tube here that we have is 1.2 meters in diameter by 7 meters in length, and it's made from a high temperature alloy. Again, this is just to give you an idea that this hole here is where that tube goes. So one of our guys there is in the picture, just to give you an idea of the scale that we're talking about. This is just an image of the carcass of the machine prior to insulating it, prior to installing the tube and instrumentation, etc. But it's just, there's something about it. It's a cathedral-like image, so I just thought I'd show it. So look, in conclusion, I think we all know, otherwise we probably wouldn't be at this conference, that we're probably on the brink of major revolutionary change in waste management, energy production, and resource recovery throughout Europe and throughout the world as well. But I think Europe is leading the way, and some of the people here at this conference probably have a good chance to be at the forefront of that. And our own journey has been filled with many insights, lots and lots of challenges and problems, but also some successes. And we're excited to take the next step towards a circular economy, which is obviously coming very quickly. And I just want to emphasize that there are cost-effective technologies, as you can see, that are available now, not in the distant future. And I'm extremely optimistic about the way things are going and what's to come. So thank you very much.
Yeah, thank you very much, Eddie. Any questions from the floor? Okay, we have questions online. No questions here, no? Okay, so the question online, Eddie, is just about scaling up the process. I mean, you've told us a lot about that already, but do you want to just address perhaps the key challenges and potential benefits of the scale-up you were talking about?
Yeah, the main challenge, I guess, is, to be honest, is probably psychological. It's from an investor perspective, where nobody wants to be the first. The world is a race to be second, I suppose you could say. And it's one of those things, once people see it out there scaled up, it'll become obvious that, why hasn't this been done all along? I don't see technical challenges as such. I see the challenges as always being financial, and coming from an unwillingness, perhaps, from certain parts of the investment community to take a little bit of a risk, So I've looked at all the technical stuff for many years. I don't, there has been problems in the past with pyrolysis systems in terms of tarring and blockages, but all those issues can be resolved quite easily, actually. And there's been a huge amount of learnings over many years. And in many ways, this type of technology is old hat. It's been around a long time, and it's probably vanished off the radar, somewhere in the middle of the 20th century, when oil and gas have taken over as energy sources. But prior to that, in times of shortage, these type of technologies were used widely. So none of this is really new. Technically, it can all be done. And in fact, it can all be done very cost effectively at small scale, which is strange. Typically, you'd have to build something extremely big, at a large scale to justify the capex involved, the capital cost of doing it. Whereas with these systems, they can actually be quite cost effective with very good paybacks at relatively small scales, you know, scales that could serve a small town. So, you know, it's very unusual that this hasn't taken off already, in my view, and I can only put it down to perhaps a lack of investment for whatever reason, and it being diverted to other renewable energy sources and so on. So, yeah, I'm not sure if that quite answers the question, but it's just my personal view. There isn't a technical issue with scaling. It's simply down to money.
Oh, that's great, Eddie. Thank you very much.
Thank you very much.